In this video, we're going to discuss related rates. Imagine that a stone is thrown into a still pond, creating a ripple. And imagine the radius of the ripple increases at a constant rate of 1 meter per second. So after 1 second, the circular ripple has an area of pi r squared, pi 1 squared, which is pi meters squared. After 2 seconds, pi times 2 squared is 4 pi meters squared. After 3 seconds, it's 9 pi meters squared. And after 4 seconds, it's 16 pi meters squared. So we can see just by looking here that we're always increasing by the area is increasing by a changing amount. The rate of change of the area varies, but the rate of change of the radius is constant. It's always 1 meter per second. So we see that although the rate of increase of the radius remains constant, the rate of increase of the area is changing. The rate of increase of the area is related to the rate of increase of the radius, and so we call it a related rate. And the rate of increase of the area is a function of time and is not constant. And there's many types of related rates in calculus. We can, like in this example here, first bullet point, imagine a stone in a pond creating a circular ripple. The rate of increase of the area of the circular ripple will be related to the rate of increase of the radius of the ripple. And if the rate of increase of the radius is constant, the rate of increase of the area will not be constant. We can imagine blowing air into a spherical balloon. The rate of increase of the radius of the sphere will be related to the rate of increase of the volume of the sphere. Now, if the rate of increase of volume is constant, which is typically the situation, we pump air in at a constant rate, the rate of increase of volume will be constant, but the rate of increase of radius will not be, because as the balloon gets bigger and bigger, the radius isn't increasing as much as it is at the start when it's a really small balloon. And third bullet point, imagine filling a cone-shaped container with liquid. The rate of increase of the height of the liquid will be related to the rate of increase of the volume of liquid in the cone. At the start, when you're right at the narrow part of a cone, the liquid seems to be rising really quickly. But then as the radius of the cone gets wider and wider and wider, the increase in the height of the liquid is not seemingly going up at the same rate. It's not constant. So the last sentence in the third bullet point there says if the rate of increase of the volume of the liquid is constant, the rate of increase of the height of the liquid won't be constant. And there's many, many, many more examples. So how do you approach a related rates problem? Some people like to draw a diagram. You want to assign a variable to each quantity in the problem. That's a function of the independent variable. And we're going to assume for the remainder of this discussion, this video, that the independent variable is time. We want to develop an equation that associates the variables with one another and then differentiate, possibly using implicit differentiation. And then we want to substitute in the given information and solve as they ask us to. So imagine we have a raindrop falling into a small puddle, creating a circular ripple, spreading out from the point where the raindrop hit, and the radius of the circle grows 3 centimeters per second. We want to determine the rate of increase of the circumference of the circle with respect to time, and then we want to determine the rate of increase of the area of the circle when the area is 81 pi centimeters squared. Well, let's solve part A. We want to let R represent the radius and C represent the circumference. So we want to get an equation of circumference in terms of radius. That equation was taught to us in grade 8 math. Circumference equals 2 pi r. So once again, this question is asking us about rate of increase of circumference, but we have information about rate of increase of radius. So we want to get a function of circumference in terms of radius. What we're going to do next is we're going to differentiate both sides with respect to t. Here's our equation. Represent both sides with respect to t. Sometimes we have to use implicit differentiation. Sometimes we don't. Well, we have the derivative of circumference with respect to time is dc over dt. We have a constant of 2 pi r, excuse me, a constant of 2 pi. We have a variable r. The rate of change of radius with respect to time is dr over dt. So we actually did not need implicit differentiation in this case, but we have a function for the rate of change of circumference with respect to time, so long as we know the rate of change of radius with respect to time, which we in fact do know. It's actually 3 centimeters per second. Okay, so we go on to the next slide, and so we've got the rate of change of circumference with respect to time is 2 pi times dr over dt. Well, since the rate of increase of radius with respect to time is 3 centimeters a second, that means dr over dt equals 3. So that means dc over dt is going to equal 2 pi times 3, which is going to be 6 pi. Okay? Now, we have to keep in mind what the units are, and the units in this case, we know circumference is measured in terms of centimeters, and we know that time in this case is measured in terms of seconds, so that 6 pi is 6 pi centimeters per second. Now, for the second part, we want to determine, again, we know the rate of increase of radius with respect to time. We want to know the rate of increase of area with respect to time. So we're going to have to get a formula for the area in terms of the radius. Well, we have such a function. We've known this one since grade 8. Area is equal to pi r squared. Now, what we're going to do is differentiate both sides of that equation. So the derivative of area with respect to time will be, what we're going to do is apply the power rule here. So applying the power rule on pi r squared, we get 2 pi r. But we're differentiating with respect to time, not with respect to radius. So we have to multiply that by dr over dt. This is implicit differentiation. Okay? So we have this formula for the dA over dt, which was given on the previous slide. That's what it equals. Now, we know that dr over dt is positive 3 from that sentence right there, but we need to know what the radius is. And to determine the radius, we're just going to have to figure out what's the radius of a circle whose area is 81 pi. That's not too tough to figure out. And once we figure out that, we'll be able to plug it in here, and we'll have our answer for dA over dt. So that's what's written here. We know that dr over dt equals 3, so we plug a 3 in right there, and we can say that dA over dt is equal to 6 pi r. Now, this 3 is measured in terms of centimeters per second, so we're going to have appropriate units at the end. But if you keep your units consistent throughout, you'll be able to determine what the appropriate units should be at the end of each question. So we have dA over dt expressed as a function of r. Our job is to determine the radius when the area is 81 pi centimeters squared. We're repeating ourselves, I know. So I'm saying 81 pi equals pi r squared, which means 81 is r squared, which means r is 9. And we can now sub that into our formula for dA over dt, and r value of 9. We get 54 pi. And we've been talking about centimeters the whole time, so area will be in centimeters squared. We've been talking about seconds the whole time for our units for time, so we can say centimeters squared per second, and that is what we get for our rate of increase of area of the circle at that moment in time when the area is 81 pi centimeters squared. Now, suppose we have water pouring into an inverted right circular cone at a certain rate. The height and diameter of the base of the cone are both 10. We want to know how fast the water level is rising when the depth of the water is 8 meters. An inverted circular cone looks like what we're showing you here. And we have a radius of 5, and because it tells us that the diameter is 10. That's what it means when it says, yeah, right here, the diameter of the base of the cone. It's inverted, so the diameter is across the top. And so that diameter is 10, meaning our radius will be 5. The height is 10. Okay? Now, what comes up next is pretty neat. Think in terms of similar triangles. We see that at a certain point, we've filled up to the red line. And when we filled up to the red line, we see that we'll get a triangle similar to when we filled up to the green line, and another similar triangle as when we filled up to the um, uh, black line. In other words, what we're saying is these angles are all the same. So this angle at the bottom and this angle here, we know this will always be a right angle. So that angle up here at the top and this angle right here at the bottom will be equal even when it's a green triangle. These angles are the same as they were a moment ago, and they're the same as they were a moment ago for this one. We've got similar triangles all the way up. And we know that on this last one, the one in front of you right now, we know that the height is 10, and we know that the radius is 5. And since we have similar triangles, we know that that's always going to be the case. That ratio of 5/10 will stay consistent throughout. And so the ratio of the height to the radius is the same for each of the three triangles, meaning the ratio of the height to the radius of the inverted circular cone will be 2 to 1, no matter how much has been filled up at any given point in the question. Okay, so now, why did we need to do all that? Because it says, how fast is the water level rising when the depth of the water is 8 meters? Well, we know the radius is always half the depth. So when the depth of the water is 8 centimeters, the radius will be 4 centimeters. Okay, so that's important to know. Now, the speed that the water level is rising, the water level is given by h, so the rate of change is dH over dt. So we would like to know this quantity right here because it says how fast is the water level rising. And we know the rate that the water's pouring in. We can think of this as the rate of change of volume, which is dV over dt. So the volume is increasing, meaning dV over dt is a positive number. There's a positive number. But we would like to know what dH over dt is. So what we're going to have to do is get a formula for volume in terms of height, then differentiate both sides, and we'll have a formula for dV over dt in terms of dH over dt. Okay? So we know a formula for volume of a cone is V equals 1/3 pi r squared h. But remember our earlier discussion that r is 1/2 of h? We're going to plug that in right here. And we're going to get that the volume of the cone is 1/3 pi times 1/2 h quantity squared times h, which is 1/12 pi h cubed. Now we've got a formula for volume in terms of height. We're going to differentiate both sides. Differentiating v with respect to t gives us dv over dt. Differentiating this quantity first by using the power rule gives us 3/12 pi h squared. But then, since we were differentiating with respect to time and the variable in question is h, we're going to have to say dh over dt. And that's what we have right here. And we can simplify 3/12 to 1/4. So we can say that our rate of change of volume with respect to time is 1/4 pi h squared times dH over dt. Now, we know that at the time in question, the height of the water is 4, or sorry, is 8. The radius is 4, meaning the height is 8. So I'm going to sub that 8 in for h. And I'm going to be able to say that, and then we also know that the volume is increasing at a rate of pi meters cubed per minute. That was stated very early on. So we can put a pi in for dV over dt, and we can put an 8 in for the height. And all we have to solve now is dH over dt, and we can do it. So pi is equal to 16 pi dH over dt ultimately. So dividing both sides by 16 pi, we see pi over 16 pi equals dH over dt. which is the same as saying dH over dt is 1/16. Since height was always measured in meters and time was always measured in minutes, we can say that the rate of change of height with respect to time is being measured in meters per minute. And so we can say that when the depth of the water is 8 meters, the water level is rising at a rate of 1/16 meters per minute.